Good morning, students. Hope you are all doing well. Welcome to the lecture 4 of quadratic expressions. Hope you have reviewed the last lecture because in the last lecture we have left with a question for what real values of x a quadratic expressions will take a positive sign or a negative sign. So this is what we are going to discuss here. In this lecture, we are going to discuss some theorems related to sign of a quadratic expressions and its related problems. And we'll discuss one more theorem, namely extreme value theorem for quadratic expressions. Let's get started. So the title is the sign of quadratic expression and the change in the signs. Here is the first theorem. The theorem goes like this. The theorem goes like this. Let a comma b comma c belongs to reals and a not equal to 0. That means a, b, c are real values. Then the roots of ax square plus bx plus c is equal to 0 are non-real complex numbers if and only if ax square plus bx plus c and a have the same sign for all real values, that is for all x belongs to real numbers. Let me read the statement once again. Let a comma b comma c be real numbers such that a not equal to 0. Then the roots of ax square plus bx plus c is equal to 0 are non-real complex numbers if and only if ax square plus bx plus c and a have the same sign for all x belongs to real numbers. Let us understand this statement. So what this theorem is telling is, if at all the roots of a quadratic equation ax square plus bx plus c are complex numbers, okay, complex numbers, then this expression ax square plus bx plus c and a have the same sign for all x belongs to real numbers actually. Okay, this is what the theorem states. And the other way is also true. If at all this ax square plus bx plus c and a have the same sign, then the roots of this quadratic expression is also, the roots of the quadratic expression are complex numbers. So it is actually an if and only if statement. Now let us understand this theorem through example. So here is our first example. So I think this example we have seen it already. So x square plus 2x plus 2. Now this thing, non-real complex roots. When does a quadratic equation has a complex numbers as a roots? If the discriminant is going to be 0. So discriminant is going to be less than 0. Let me calculate delta. Delta is what? B square minus 4ac. B square minus 4ac is what? It is 2 square minus 4 into a into c. That is 4 minus 8, that is equal to minus 4, which is less than 0. That means since delta is less than 0, we can conclude that this quadratic expression has real roots. So this quadratic expression has complex roots actually. Then what is that it is telling? The quadratic expression ax square plus bx plus c and a have the same sign for all x belongs to real numbers. This is what it tells. Now let me see, and this is the example that we have seen actually. This example we have seen it already. And we know that this x square plus 2x plus 2 can be written as x plus 1 whole square plus 1. Okay, so what it is actually telling is, since the discriminant is negative, in turn the roots becomes complex numbers. Accordingly, by that theorem, this expression and a have the same sign. Here, what is the sign of a actually? A value is equal to 1, which is positive. So if a is positive, then the expression is also positive. The important conclusion here is, for all x belongs to R, for all x belongs to real numbers, this x square plus 2x plus 2 is going to be positive. This is what we have seen in the last lecture. Now, let me discuss the next example. Here, the discriminant here. Let me write what is A. A is minus 1 and B here is 4 and C here is minus 5. What is the discriminant here? Discriminant is 4 square minus 4 into minus 1 into minus 5. So this is 16 minus 20, that is equal to minus 4, which is negative. So the roots of this quadratic equation, quadratic expression, are complex numbers. Then what does this theorem says? And a is equal to minus 1, which is negative sign. This implies the conclusion here says minus x square plus 4x minus 5 is going to be negative for all x belongs to real numbers, as a is minus 1, which is a negative number. This is what this theorem says. Okay, let me verify this. Okay, now this minus x square plus 4x minus 5 is equal to, this can be written as minus of x square minus 4x plus 5, and this can be written as minus of x square minus 2 into 2x plus 5. I can write it as 4 plus 1. This can be written as this x minus 2. Okay, let me. So here this can be written as minus of x minus 2 whole square plus 1. So whatever the real value are going to substitute here, and it is going to be negative. That also we have verified. So we have understood this theorem. Let me quickly go through the proof of this theorem. Okay, here we have this ax square plus bx plus c can be written as a into x square plus b by ax plus c by a. Now is ax square plus bx plus c divided by a. I have written this a in the denominator here, and this can be written as x square plus b by a into x plus c by a here. Okay. Now this I am going to rewrite it. Okay. So how am I going to rewrite it? Let us see. So what am I doing here? This expression I am writing as it is. I am actually completing the square. Actually, this trick we have already discussed of completing the squares. I am adding and subtracting in order to complete this square actually. Okay, let me see. Okay, what am I doing is I have completed the square. I have completed the square here, and the leftover terms are c by a minus b by 2a whole square, that I have written b square by 4a square actually. Now if I rewrite this, what am I going to get is x plus b by 2a whole square plus 4ac minus b square. and this is anyway a positive quantity, a non-negative quantity, and this I have to check 4ac minus b square. If you look at that carefully, this is nothing but minus of the determinant actually. So this is what? This is ax square plus bx plus c divided by a is positive they are telling, because b square minus 4ac becomes negative, implies 4ac minus b square is positive. So this is a positive quantity. This is a positive quantity which is greater than or equal to 0, and this is also a positive quantity. Okay, this is strictly positive now. So sum of two positive quantities is again a positive quantity. This is what they have written here. So ax square plus bx plus c divided by a is positive. So when do you say that the ratio of two terms is positive? Here the ratio a by b, the ratio a by b is positive if and only if A is positive, B is positive, or A is negative or B is negative. That means this expression, this is what the theorem says. This expression ax square plus bx plus c and A, in both the cases, see here what they are telling is a by b is positive if a is positive, b is positive, or a is negative or b is negative. That means what? Both a and b must take the same sign here. So in the place of a and b, you have this ax square plus bx plus c and a here. Now, that means this expression and this expression, these two must take the same sign. You can find out the value of a easily by looking at anyway, it is given in the quadratic expression. By looking at this expression, you can tell this expression is positive or not. If this is positive, this is positive. If it is negative, this must be negative for all x belongs to real numbers. Okay, here hence the theorem actually. This is simply just the proof of the theorem. The proof is very easy. Okay, let me discuss the next theorem here. The next theorem here is the statement of the theorem goes like this. Let A, B, C belongs to reals and A not equal to 0. If the equation ax square plus bx plus c is equal to 0 has equal roots, then ax square plus bx plus c and a have the same sign for all x belongs to reals except this number minus b by 2a. I hope you get this quantity. What is this quantity actually? Given that the quadratic equation has equal roots, actually this minus b by 2a is the root of that quadratic expression, quadratic equation actually. Okay. Now let me understand this theorem with the help of some examples. Okay. Here is an example. This example we have seen it already. Okay. Uh, Discriminant for this expression is b square, that is 2 square, minus 4 into a into 1, that is going to be 0. If delta is 0, implies the roots are real and equal. Roots are real and equal. So the roots are equal. In this case, we have seen this x square plus 2x plus 1 can be written as x plus 1 whole square. And what is the sign of A here? Sign of A is positive. Sign of A is positive means by that theorem you can say this expression is also takes the same sign as that of A. That means ax square plus bx plus c is also positive for all x belongs to reals minus b is 2 divided by 2 into 1, that is for all x belongs to R minus 1. Minus 1 actually is the root of this quadratic expression. So this expression is going to take a positive value. This expression will be positive, okay, for all real values of x except minus 1 here. Okay, now let us look at the second example. The second example here is, here the delta value here is b square, that is 4 square, minus 4 into a, that is minus 1, into minus 4. So this is 4 square, that is 16. 16 minus 16, that is going to be 0. That is going to be 0 actually. So what is the sign of a here? What is the sign of a? It is minus 1, which is negative. So according to this theorem, these conditions are met actually. This quadratic equation has equal roots, and the sign of a is negative. This implies this minus x square plus 4x minus 4 is going to be negative for all x belongs to reals minus b by 2a, that is minus 4 divided by 2 into minus 1. So that is r minus 4 by 2 is actually 2. Okay, so this expression is positive for all x belongs to R minus 2 actually, except for real number 2. For all other reals, it is taking, sorry, it is taking, it must take the negative sign actually. I have written it wrongly here. Okay, here it takes negative sign. This is negative because this a is a negative, a is minus 1, thus minus 1 is a negative value, so this expression also should take a negative value. So for all x belongs to R minus 2 reals except 2, this expression is negative. So I hope you have understood this. And one more thing is to convince minus x square. Okay, let me write this. Minus x square plus 4x minus 4 can be written as minus x square minus 4x plus 4, and this can be written as minus of x minus 2 whole square. Now you can see whatever the real number I substitute, this quantity is going to be positive and minus 1, so this quantity is going to be negative. Okay, except for x is equal to 2, that quantity becomes negative actually. Okay, let us quickly go through the proof of this theorem. Okay, proof of this theorem. Anyway, we have this ax square plus bx plus c. In the last proof also we have seen it. This we can write it as, by taking common a, we can write it like this. Now we are writing this a in the denominator, and the leftover quantity becomes x square plus b by ax plus c by a. Now this quantity, to complete the square, what am I doing? I am adding and subtracting b by 2a whole square on both sides. So I have completed the square. Now let me rewrite this expression. This is going to be x plus b by 2a whole square plus 4ac minus b square, and this quantity is actually, this quantity is 0 because the roots are equal. The discriminant is going to be 0. Okay, so Now, what did you get actually? Ax square plus bx plus c divided by a is equal to a squared quantity. Now, what is the conclusion? As ab square minus 4ac is 0. Now, this is going to be greater than or equal to. Why it is equal to greater than or equal to 0? Because x is equal to minus b by 2a. This becomes 0. So, this is greater than or equal to 0. So, what is the conclusion actually? The conclusion here is the ratio is taking a positive sign. As we have seen in the last theorem, the ratio is positive if and only if both the numerator quantity and the denominator quantity take the same sign. If numerator is positive, denominator must be positive. If the numerator is negative, the denominator must be negative. So it all depends on the sign of A actually. Okay. This is the proof of theorem. To hope you have understood the theorem, you revisit you revisit again. If you have any doubts, you can ask me in the next class. Okay. Now we are going to discuss the third theorem. We have discussed two cases earlier. One is with delta negative and other case with delta positive. Here delta must be, in this case the delta must be positive actually. Let me read out the statement of this. Let A, B, C belongs to real numbers and A is not equal to 0 such that ax square plus bx plus c is equal to 0 has real roots alpha comma beta with alpha less than beta. Then we have some conclusions here. What is the conclusion here? For alpha less than x less than beta, this ax square plus bx plus c and a have opposite signs. This is what you have to understand here. It has opposite signs. And for x less than alpha or x greater than beta, ax square plus bx plus c and a have the same sign actually. Okay. So it has the opposite sign and it has the same sign. So when is it possible? Let me explain it with the help of a diagram. Now on a real number line, let alpha comma beta be situated like this. Since alpha is less than beta, the situation will be like this. Okay. Now, so here if A is positive, then expression. So where this expression, let me write is let f of x is equal to ax square plus bx plus c. Okay. Now, if A is positive, what does this statement tells? So the first statement is in this region, this expression ax square plus bx plus c and a have opposite sign. If A is positive here, then f of x will be negative here. Okay. So if x is less than alpha or if x is less than alpha or x greater than beta, that means in this region, okay, this expression and a have the same sign. Already the sign of a is already fixed here. Okay. Now, so in this region and in this region, this f of x will be negative and f of x will be negative. Now we have another case. If a is less than 0. Okay. Now what are the conclusions here? In this case, this f of x will be positive and f of x will be negative. So here it takes 1 minute. 1 minute. If it is positive, okay. Okay, let me rewrite this. So let me explain. Okay, let me explain the statement of the theorem graphically. Okay, let f of x is equal to ax square plus bx plus c. Okay, let me draw a real number line. Okay, here is my alpha located and here is my beta. Why I have written like this? It is given that alpha is less than beta. Okay, now there are actually three regions. One is x lies between alpha and beta. Now the other region is x less than alpha, and one more region is x is greater than beta. This is the region x greater than beta, and this is the region where x lies between alpha and beta, and this is x is less than alpha. Okay, now there are actually two cases. If a is positive, what happens? If a is positive, what happens? Let us see. The conclusion here is if 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 x lies between alpha and beta, this expression and a have opposite signs. That means if a is positive, this expression is negative. If a is negative, this expression will be positive. Okay. Now, since a is positive in this region, this expression x is going to be negative. So, f of x will be negative here. Now, in this region, x is greater than beta or x less than alpha. Okay, x less than alpha or x greater than beta both have the same sign. That means what? That means in this region, this f of x is going to be, since the sign of a is positive, and in this region f of x is positive, and in this region f of x is also positive. So only in this region it becomes negative, in both other regions it is positive. Let me discuss the next case. If a is negative, now this time a is negative. Now in this region, that means in the alpha lies between, that means x lies between alpha and beta, both takes the opposite sign. Since already a is negative here, since already a is negative, then f of x must be positive here. Okay, and in this region x less than alpha, x greater than beta, since already a is negative, so f of x will be negative here. F of x will be negative, and even in this region also f of x is negative. Okay, so this is how we can understand with the help of a diagram. This is what the theorem statement tells actually. Okay, let us quickly go through the proof of this theorem. Okay, before going into the proof of this theorem, we have some examples here. Okay, so this expression, okay, x square minus 5x plus 6 here, of course, anyway, the roots of this expression are 2 comma 3. Alpha is equal to 2 and beta is equal to 3. So when is this expression positive and when is this expression negative? Let us find out this quantity. Okay, here the alpha and beta are located on a real line. Okay, now what is the sign of A here? A is going to be 1. A is going to be 1, and in this region it takes the negative sign. Okay, this is negative. Okay, now let me write this f of x is equal to x square minus 5x plus 6. So in this region, this f of x, since it is positive, this must be negative here, and here it is going to be positive. Okay, so what we can say from the theorem is in the region from 2 to 3. Okay, that means if x value lies between 2 to 3, the expression is going to be negative. The expression is going to be negative if x is less than 2 or x is greater than 3, the expressions will take the positive sign. Okay, let me see the next example. Okay, in the next example, the roots here are x is equal to minus 1 by 3. So that is alpha is equal to minus 1 by 3 and beta is equal to 1 by 2. Okay, so let me draw a real number line, and here I am locating my alpha and here I am locating my beta. Now let me write g of x is equal to 1 plus x minus 6x square. Okay, now in this region, since what is the sign of a here? A is equal to minus 6, it is going to be negative. So since it is negative, what is our conclusion here? In this region, both f of x and a takes the opposite sign. So f of x will be, since it is negative sign, it is going to be positive here. And in this region, this f of x is going to be negative. Okay, so we have got the region in which, okay, we can write it formally. F of x will be positive for all x belongs to minus 1 by 3 to 1 by 2. Okay, and it is negative for all x belongs to, this region can be written as minus infinity to minus 1 by 3 union 1 by 2 to infinity. Okay, so with the help of the theorem we could answer, we can tell the sign of the expression with the help of this theorem. Let us quickly go through the proof of theorem. Okay, so we know that ax square plus bx plus c can be written as a into x minus alpha into x minus beta. So in the previous two cases we have written this expression in some different manner, and here I have written in a different manner because in the hypothesis of the theorem uh, it has been given that this equation has two real and distinct roots, namely alpha and beta here. That's why I could write this ax square plus bx plus c as a into x minus alpha into x minus beta. Okay, I have written this a in the denominator, and the leftover expression is x minus alpha into x minus beta here. Okay, Now this is our first case. If x lies between alpha and beta, then okay, x minus alpha will be positive and x minus beta is going to be negative. Obviously, okay, let us understand this. So here is alpha and here is beta. Now the x is here. X is greater than alpha. So x minus alpha will be positive. X is less than beta. X minus beta will be negative here. So what is the conclusion here? This x minus alpha into x minus beta becomes negative here. Whenever x lies in this region, this product is going to be negative because it is positive and this is negative. A positive quantity into a negative quantity. So this is positive quantity and this is negative quantity. The product of positive quantity and a negative quantity is a negative quantity. Okay, that's what they have written. This implies this ax square plus bx plus c divided by a is less than 0. When is the ratio less than 0? If both numerator and denominator have the opposite sign. Okay, this is negative. If both numerator and denominator have opposite sign. Okay, that means what? In this region in this region this quantity is going to be negative, implies this expression and a will take the opposite sign. This is what the theorem states. Okay, the next case is x is greater than beta. That means, okay, in which region we are considering. It means, let me write alpha, let me write beta. We are in this region. We are talking about this region. We are in this region. X is greater than beta. Anyway, it is greater than alpha. X minus alpha is greater than 0 and x minus beta is also greater than 0. Then you can see this x minus alpha and x minus beta will obviously be positive. This x minus alpha and x minus beta is obviously positive, but this expression is equal to what? Ax square plus bx plus c divided by a, and this ratio is positive. When is the ratio positive? Both expression and a takes the same sign here. Okay, so we have proved the theorem in this case. Similarly, in the other case also we can prove the theorem. So we have proved this theorem in three different cases. One is the case one, x lies between alpha and beta whenever x greater than beta and greater than alpha, and the other case is this one. Okay, now alpha is here, beta is here. Now you should be in this region. X is less than alpha and less than beta. Now similarly we can prove the above theorem in this method. Now I hope you have understood the three theorems. Now let us do some problems based on these three theorems. Okay, let me discuss a problem based on theorem 3. Here is the problem. Discuss the signs of below given quadratic expressions where alpha less than beta, alpha comma beta belongs to R. So here is the question. Okay. Now what we need to do here is we have to discuss the signs of this quadratic expressions when where alpha comma beta belongs to R, alpha is less than beta. Now this product can be written as x square minus of alpha plus beta into x plus alpha beta. Now it looks like a quadratic expression, and here this is minus x square plus x into beta plus alpha into x minus alpha beta. Okay, now let me write ABC values here. Here A is equal to 1, B is equal to minus of alpha plus beta, and C is equal to alpha beta. And here A is equal to minus 1 and B is equal to beta plus alpha, and C is equal to minus alpha beta. Okay, now here the roots of this expression are alpha comma beta. Therefore, by applying the theorem, so let me draw a real number line here. Here it is alpha and here it is beta. Okay, now let me shade this region. Okay, now A is equal to, okay, let my f of x is equal to the given expression x minus alpha into x minus beta, let us say. Okay, so A is equal to 1, which is positive. Then I have the following conclusions. Here my f of x will take the opposite sign. This is less than 0. Here in these two regions, f of x is going to take the same sign. So it is positive here and f of x is positive here. So the conclusion here is f of x is equal to x minus alpha into x minus beta is negative if x belongs to the interval alpha to beta, and f of x is equal to x minus alpha into x minus beta will be positive if x belongs to this region, that is x belongs to the interval minus infinity to alpha union beta to infinity. So please do remember. The next topic that we are going to discuss is the extreme values of a quadratic expressions. What are the extreme values? The extreme values of a quadratic expression are also called maximum and minimum values. Okay. Now the question is, given a quadratic expression, how to find out the extreme values? To find out these extreme values, we are going to state and prove a theorem. Here is the statement of the theorem. Suppose that a comma b comma c belongs to R and a not equal to 0 and f of x is equal to ax square plus bx plus c. So this is a given quadratic expression. Then we have the following conclusion. What is that? If a is greater than 0, then f of x has absolute minimum at x is equal to minus b by 2a, and the minimum value here is 4ac minus b square divided by 4a. The next conclusion is, if a is less than 0, then f of x has absolute maximum at x is equal to minus b by 2a, and the maximum value is 4ac minus b square divided by 4a. And the terms is absolute minimum and absolute maximum that we have studied in the first year calculus course. Anyway, I hope you remember these terms: maximum and minimum, absolute maximum and absolute minimum. Okay, now let us quickly go through the proof of the theorem. Here is the proof. Now we know that f of x is equal to ax square plus bx plus c can be expressed as the sum of the following two terms. In the earlier theorems, we have used this result. Okay, this ax square plus bx plus c can be written as the sum of these two terms. Okay, Now, if a is positive, then f of x is greater than or equal to 4ac minus b squared divided by 4a. How is it possible? Remember, a is positive here. Given that a is positive, now a positive and this quantity is also positive. So positive into positive quantity is again a positive quantity. Okay. So this is going to be positive. This is going to be positive. Okay. Whenever this is positive, we are adding a positive quantity to this number 4ac minus b square divided by 4a, then obviously this quantity is going to be, this combined expression is greater than 4ac minus b square because we are adding some positive quantity. Okay, let me explain it with the help of an example. This a plus p is greater than p if a is positive. Because we are adding a positive quantity to p, so this combined expression is greater than p actually. Okay, hope you have understood this. Now let us come back to the next step. Now f of x is, see, we have this f of x is greater than or equal to 4ac minus b square divided by 4a. Now at x is equal to minus b by 2a, what is happening here? Let us see. At x is equal to minus b by 2a, what is f of x value? That means I have to substitute x is equal to minus b by 2a. If I substitute, this quantity is going to be 0. We are going to get 4ac minus b square divided by 4a. Let us see what it is. Yes. So this is 4ac minus b square divided by 4a. Now, what is the definition of absolute minimum? Okay, absolute minimum means this f of x value is greater than or equal to this particular quantity and and it is attained at the point x is equal to minus b by 2a. Therefore, by the definition of absolute minimum, okay, f of x has absolute minimum at x is equal to minus b by 2a. So here is that statement: f of x has absolute minimum at x is equal to minus b by 2a, and the minimum value is 4ac minus b square divided by 4a. Okay, let us try to recapitulate what is absolute minimum once again. Suppose in a class of 50 students, we say that some student is shortest fellow or absolute minimum or a shortest guy. When can you say that that guy is a shortest guy? If everybody else's height must be greater than or equal to that height, then he becomes the shortest guy. In a similar manner, f of x, this quantity, when it is going to be minimum, if f of x is greater than or equal to this quantity and it is attained at some quantity, then it is going to be absolute minimum at x is equal to minus b by 2a. Same is the case with absolute maximum. Now let us see the proof of the second statement. If a is less than 0, then f of x is less than or equal to 4ac minus b square divided by 4a. Okay, let me explain this. See, like a is a positive quantity, a minus p, see, is less than a if p is greater than 0. That means we are subtracting some positive quantity from a, obviously it will be less than a. This is what they have used here. Okay. Now, similarly, when x is equal to minus b by 2a, then f of x is going to be 4ac minus b squared divided by 4a. Therefore, see this guy, the f of x is less than or equal to this quantity, and it is attained at x is equal to minus b by 2a. So, by the definition of absolute maximum, f of x has absolute maximum at x is equal to minus b by 2a, and here it should be the maximum value. It is not minimum, it is maximum value. and the maximum value here is 4ac minus b square by 4a. Okay, let's do some problems on the extreme value theorem. Here is the problem. Find the extreme values of the following expressions as x varies over r. Here is the first question. Let us try to write the solution for this. Okay, solution. Here, let me write it in a proper format. It is minus x square plus 12x minus 32. So here a is equal to minus 1 and b is equal to 12 and c is equal to minus 32. So a is equal to minus 1, which is negative value. Then by extreme value theorem, let me assume it as f of x. Okay, by extreme value theorem, f of x has, what does f of x has? If a is negative, f of x has absolute maximum at x is equal to minus b by 2a. Now let me find out what is that x. X is equal to minus b, that is minus 12 divided by 2 into a, that is 2 into minus 1. So it is 12 divided by 2, that is equal to 6. So f attains, you can say, f attains absolute maximum at x is equal to 6. So, and its value is f of 6 is equal to minus 6 square plus 12 into 6 minus 32. So this is minus 36 plus 12 into 6 is 72 minus 32. So this is minus 68 plus 72 and this value is 4. So the maximum value here is 4. So the maximum value is 4. Okay, now let us try to find out the solution for this. Here is the solution. Here my capital A is A, my capital B is small b, and capital C is A again. Okay. Now there are two cases here, as there is no information given. Of course, they have to give A not equal to 0 here. As the sign of A is not given, we'll assume cases if A is positive. If A is positive, okay, by extreme value theorem, f of x has absolute minima at x is equal to minus b divided by 2 capital A. Okay, that is minus b divided by 2a, and the value is 4ac minus b square divided by 4 into a. So that is 4 into capital A is small a, capital C is small a, minus b square divided by 4 into a. So that value is going to be 4a square minus b square divided by 4a. Okay. So why I have taken capital A, capital B means because these two small a's are repeated. So to avoid the confusion, I have taken capital A and capital B and capital C. Similarly, if small a, or maybe you can take here, yeah, if small a is less than 0 by extreme value theorem, f of x has absolute maximum at x is equal to minus b by 2a, and its value is, already we have computed that, it is 4a square minus b square divided by 4a. So it all depends on the sign of a actually. If a is positive, the same value is going to be absolute minimum. If the a is negative, the